Hi, welcome back, and we are going to talk about mainly two sorting routines to add to our collection, selection sort and insertion sort. Along the way, we are going to need to talk about compareTo, because we're going to need to compare two objects to each other and see which one's larger. And as a part of that, we're going to be doing the searching of already ordered arrays. So we want to keep them in order. We're going to look for a particular object or primitive data type inside. So the objectives, we can come back to this at the end of the video, but we're going to talk about compareTo, how it's used in searching, how our class uses it, and how what my expectations are compared to how the AP committee will use it. They're actually both ways are definitely important. We'll talk about selection sort and have practice. We'll talk about insertion sort and have practice, and talk a little bit about the difference between all three sorting algorithms: selection, insertion, and bubble, and then understand why we call these three quadratic sorts. When we are putting something in order, we need to see if something's larger than something else. But with an object, we don't have the capability of using the less than, greater than, or equals operators. There's two ways to look at this. And one way is to say that if a class, like person or rectangle or any of our classes, implement the comparable interface, we'll talk a little bit about that later, then they must define the method compareTo. And the method compareTo must be defined in a very specific way. It must be public because we need to use it, right? It must return an integer. You cannot change the identifier whatsoever. The idea about compareTo is that you have some standards that are always the same. When you looked at the signature in this particular slide, you notice that it returns an int. Now, what is the value of that int? If the left-hand side object, the object that is invoking it, compared to the object that is passed, so I'll call this the left-hand side and the right-hand side. Basically, if the left-hand side is less than the right-hand side, you return a negative integer. It does not need to be -1. It could be, but you should not generalize that it would be -1. We'll go to the bottom one. If the left-hand side is greater than the right-hand side, you're going to return a positive integer. And once again, I just go left to right. That's the way that I remember it. If you have not returned a negative integer and you have not returned a positive integer, then you must have returned 0. And what that means is it's not greater than, it's not less than, it is equal to. Let's look at what some real outputs of compareTo with strings would be. We have string str and it's assigned Mary. And so then we print out str, which is Mary, compareTo Suzanne. And these are ordered, as we have talked about, they're alphabetical. Mary is less than Suzanne because uppercase M is a lower ASCII value than uppercase S. And str is less than Suzanne, therefore we expect a negative number. This one particularly prints out -6, but we don't really care about that. The value, we care that it's only negative. str compareTo Mary, well, they're exactly the same, Mary and Mary, and so they are equal to each other, so it prints out a 0. System.out.println str compareTo Bob, well, Bob is alphabetically before Mary, therefore we would expect that str Mary is greater than Bob, therefore it outputs 11, a positive number. This says that if you run this on your home system, maybe you'll get those values that I showed on the other screen, -6 and 11, or maybe you'll get something else. But what is definitely important is that you are looking for positive numbers or negative numbers or 0. One way to think of implementing compareTo is like the AP committee will ask us to do, but we don't have the tools yet to really fully discuss that. They will say if a class like student or like rectangle implements the comparable interface, then that means that you have had to have include a compareTo method, which is true. But we'll talk about that later. A second way, and the way that we're going to do it, is we will have practice implementing compareTo with different objects. And our signature will be the same. It will be public. We will return an int. compareTo will be written just like this, and we will take the other object. Just like in this particular case, you had a string compareTo string. Okay, you're going to compare to the same object. Now let's talk about selection sort, and we'll talk about like the general idea of it first. Okay, and so selection sort is a different algorithm than bubble sort, and the general idea for selection sort is we keep track of the index of the smallest data value, and we don't swap every time something's out of order. We say, let's start off with one index, and then we will go through the array and we will see, are there elements that have lower values? If so, reassign the index and keep track of that. And then at the end of the inner loop, we are going to exchange that value. So here's how this particular one works, and then I'm going to also pull up a diagram. Let's say that you have the lowest index here and the highest index here. So there's 5 elements. So this is index 0, 1, 2, 3, 4. And the way that our sorting algorithm with selection sort is going to work is it is going to place the lowest value at the lowest index. So we're going to look at this and say, let's take 4 to be the smallest value so far. Is 2 less than 4? Yes, so reassign the index. Is 5 less than 2? No, do not reassign the index. Is 1 less than 2? Yes, reassign the index to right here. Is 3 less than 1? No. And so we are going to take 1 and 4 and swap them. Thus our new ordered array. 2 comes over, 5 comes over, 3 comes over. 1 has been placed, and that means that it's not going to be revisited. We know that that is the lowest value. So we start here and we say, at this index, let's keep track of this index and assume this is the lower value. Is 5 lower than 2? No, don't reassign. Is 4 lower than 2? No, don't reassign. Is 3 lower than 2? No, don't reassign. So in this particular case, no swap is made. 2 was already in the right place. The 5 comes over, the 4 comes over, the 3 comes over. The blue notes that it's already placed and won't be revisited. Now we say, okay, let's start right here. The index of the outer loop starts at this index, which would be 0, 1, 2. Let's start at this, and let's say that the lowest value is 5. Is 4 less than 5? Yes, it is. Therefore, we replace the index. Is 3 less than 4? Yes, it is. Then we replace the index. So 3 and 5 swap with each other. And here on the very last traversal of the inner loop, we say we take 4 to be the lowest value. We say, is 5 lower than 4? No, no swap, and those move over. In order to do this, let's look at some actual code for selection sort. It's actually a void method. Let's ignore the fact that it's static. We don't really need to pay attention to that. And it accepts one integer array. You see that right here, if you look at overall of this code, it only has one for loop. But we've taken a little bit of a shortcut and we've split up some of the code. This is actually the outer loop, and we traverse the outer loop from 0 to strictly less than the length minus 1, just like we did in bubble sort. But where is the inner loop? Let's look at this. Int min index is assigned find minimum. We pass it our integer array, and we pass it I, the index of where we are currently in our outer loop. So let's look at this find minimum. Find minimum, it accepts an integer array and an integer, and it's named first. making it be the first index that it will start off at. And it has this code line right here. Int min index is assigned first. And let's see how they're going to use that. We have another for loop. So really, in disguise, this is the inner for loop, because switching back to this is the outer for loop. It called min index. What is min index? Min index is a method that contains another loop. So this is the inner loop, just a little bit disguised compared to bubble loop. So we start the inner loop at first plus 1. First, remember, was the index of the outer loop. So we're looking at the next one, and we're going strictly less than the length, so all the way to the end. And we're checking if a of I, okay, I is the loop control variable spinning around in this loop, is less than a of min index, reassign min index. So min index is going to hold the index of the lowest element of the array in the part that you're traversing. And then we're going to return min index. So before I bring up a little diagram, let's look at that. So the outer loop starts at 0, goes to 1 less than the end of the array. It calls the inner loop, and the inner loop spits back the index of the lowest value. And this one says if min index does not equal I, if the element at the lowest value, which has the lowest value, is not at the same place as the outside loop, then swap them. And I'm not gonna, and let's just take this to be a swap routine. You're swapping the contents of, in integer array A, I, and min index. So let's see what that really means. Let's say that we have this 8-element array, and let's keep track of min index. Okay, so it starts at the very top index. Okay, so this starts at 0, and it basically asks, is 6 less than 5? No, don't reassign. Is 2 less than 5? Yes, reassign min index. So far, we have the lowest value of 2. Now we're going to compare all of the new values with the lowest so far. So we're going to keep going down. Is -1 less than 2? Yes, it is. Reassign min index. Is 3 less than -1? No, don't reassign. Is 6 less than 1? No, don't reassign. Is 4 less than -1? No, don't reassign. Is 0 less than -1? No, don't reassign. And so this code says, actually let's write just a little bit more on this. I is the value of the outer loop, the index of the outer loop, and it is 0. And I is 0 and min index is 3. I is 0 and min index, find minimum, returned of 3. And so 3 does not equal 0, therefore swap the contents of just what's in 0 and min index. So let's pull that over and see what that looks like. And so the contents of 3 and 0 swap. So this is now -1 and this is now 5. And let's get a new color. And so we have completed one traversal of the inside loop, and this is not going to change. The lowest value was placed at the lowest index. So now the outer loop chunks up. It was 0. It is now 1. So these are all gone. Min index is now 1. And it says, is 2 less than 6? Yes. So min index is reassigned. Is 5 less than 2? No. Is 3 less than 2? No. Is 6 less than 2? No. Is 4 less than 2? No. Is 0 less than 2? Yes. Min index is reassigned. Oops, forgot to increment this. That was incremented to 1. 7 does not equal 1, therefore 7 does not equal 1, therefore the contents are swapped. The contents of 7 and 1 are swapped. This becomes 0, this becomes 6. Okay, and then we would ramp that up to 2, and we would start all over again. Notice that every single time min index starts at the outer value of the index because that is the one that was passed. Okay, so we won't do the rest of this, but this would start at index 2 because that's the value of I. Okay, so let's walk through the code for insertion sort, and then I'm going to take you back to that diagram and use the same array and talk about how insertion sort works. When you think about the algorithm of insertion sort, you think about being dealt a card, one card at a time, and sticking it in your hand, and all you care about is the order. So you have 2 cards that you pick up and you compare them. Are they out of order? If so, fix it. And then you pick up a 3rd card and you do the same thing and you decide where does it go. Okay, but you do it a little bit more methodically, but that's why it's called insertion sort. Let's look at this. It looks a little bit more complicated, but when we boil it down, it's just a little bit of a different take on sorting than the other 2. So we have 2 integers, item to insert and j. We have an integer array. So item to insert is going to be a placeholder. J is going to be one of the loop index values. We have a Boolean value like we talked about with the early kickout of bubble sort. It's called still looking. And so the outer loop is this for loop, and the outer loop index value is k. It starts at 1, which is a little different, and goes to the last element of the array. So instead of starting 0 and going to the next to the last, it starts at 1, the second element, and goes to the very end. And then this says walk backwards, and you're finding the insertion point. So let's see what the heck that means. You take the value that is in the index at this value of the outer loop, k, and then you assign this other index value, which is the index, the loop control variable of the inner loop, a for loop and a while loop. And you always start that out as 1 less than the outer loop. Still looking right before we enter the inner loop is assigned true. And this says while j is greater than or equal to 0, because it's going to be decremented, while j is still within the index bounds of the array and the Boolean value is true, do stuff. Okay, we compare if one's less than the other, and then we maybe reassign, and then we decrement. Okay, so this is the inner loop. We do something with a Boolean, and then we increment the outer loop. So let's see how this works on this little diagram. So I'll kind of be flipping back and forth from this code to this diagram. We looked at this and we see that k will start at 1, go to 2, 3, 4, 5, 6, 7. Remember that I said that this is like a deck of cards and you have 2 values, 2 cards. You put those in your hand and you order the 5 and the 6. Then you ask, where does the 3 go relative to the 5 and the 6? And the 3 would go, of course, above both of those. And then you ask, where does the 4 go relative to all those? You put the 4 in your hand. You put the 2 in your hand in the right place, and the 6 in the other 4, and the 0. So unlike the other loops, the inner loop for this sorting algorithm starts out very small, only compares 2 at the very beginning, then it grows. The other ones shrink. So let's follow this a little bit. And the first value of k is 1, like we talked about, so that's going to be a 1. And then the first thing that it does is it takes the value of a of k and it sticks it in a placeholder. So the value of a of 1 So the value of a of 1 is 6. So we're looking to see where do we insert this 6. J is always starting out at 1 less than k, and then we decrement each time through the inner loop. So J starts out at 0. We have a Boolean that we will mention, but we won't keep track of with the memory. We have a Boolean called still looking. Basically, have we found our place yet? While J is greater than or equal to 0, and it's 0, so we're going to go in this once. Still looking is true, so we go in here. If item to insert, if 6 is less than a of j is less than 5, is 6 less than 5? That's false. So there is no reassignment, and still looking changes to false. Okay, we're still inside the while loop. This is true, but still looking is false. Therefore, we go down to here and we say that item to insert is assigned to a of j plus 1. Well, in this particular case, that doesn't really do very much because item to insert is 6 and 0 plus 1 is 1. So we're just going to put the 6 right back where it was. Okay, so that's not too exciting. So we go to the outer loop. We ramp k up to 2. J starts off at 1 less than 2 always. Item to insert is the value of the current value of k, which is 3. So we are looking to place the 3. This will be a little bit more exciting. So 1 is greater than or equal to 0, and still looking is true. If 3 is less than 6, the contents of a of 1 go into the contents of a of 2. So this is a little bit weird feeling. Okay, the contents of a of 1 go into the contents and overwrite what used to be an a of 2. So here's the good thing. We kept track of item to insert, so we have that value. We haven't lost it, and that was the purpose of that. Okay, j minus minus, j decrements, and we go back here. J is equal to 0, and still looking is true, so we enter the while loop. Is 3 less than 5, the value at index 0? Yes, 3 is less than 5. This is true. Therefore, we do the same thing. We take the 5 and we overwrite the 6. We decrement j. It is now negative 1. And we go to the top of the inner loop. J is not greater than or equal to 0. This is false. Therefore, we kick out of the loop, and we are right here. Item to insert is assigned a of j plus 1. Okay, well, that's fine because j plus 1 is negative 1 plus 1, which is 0, and that's where we wanted to put the 3 in the first place. So we are done with the inner loop. We walk back and we increment k to 3. J is starting off at 1 less than k. Item to insert is starting off the contents of the index of the variable k, which is 4. We're going to place the 4. We're going to do the same thing. I'll get a different pen color. Let's see. Guess I'll do black. Okay, item to insert is 4. We ask, is 4 less than 6? Yes, it is. So we overwrite the, I'll go to the left. We overwrite the 4, and that is now a 6. We decrement j. Is 4 less than 5? Yes, it is. We overwrite this. This is no longer 6. We decrement j. Is 4 less than 3? No, it is not. This is the first time that we are inserting a card kind of in the middle of the rest of the card. So 4 is not less than 3, right there. Therefore, this is false. So we change still looking to false. We have a false Boolean right here. We are done with the inner loop. And let's see if this turns out correct. Item to insert, which is 4, is assigned to a of j plus 1. J has the value of 0. 0 plus 1 is 1. Therefore, at index 1, we assign item to insert. And I'm not going to do the rest of them. You can see that the 3, 4, 5, and 6 are already ordered. The 2 would go all the way down. Each one of these will come down successively, and you would do that until the very end. And then the last 2 slides, I just bring up compareTo because we can do this same sorting without hardly changing any of the algorithm. We can do it for objects. We can say we're looking for the minimum, the same find minimum that we used in selection sort, and here's how we would do it. What we can't do is we can't use this less than sign. So this is find minimum. It's returning an integer and returning the index of the lowest value. Let's look at and see what's the same and what's different. In fact, everything's the same except this is an object. Okay, and this is just a generic object. But the only difference is right here. Instead of using less than, we say this object dot compare to this object, the contents, which is an object. We ask, is left-hand side less than right-hand side? If it's less than 0, we reassign it. If it's equal to or greater than, we would not reassign it. But look and pay attention to the fact that we're not looking for a specific number. We are just looking for the fact that it is negative. Okay, that's all. I'm going to go back to the objective slide and let you look at that for just a minute. No song today. And it occurred to me, looking at this objective slide, that I never talked about the phrase quadratic sort routine. And what that means is that every single one of these sorting algorithms had a nested loop in them. And why we call that quadratic, let's look at the insertion sort routine. So here's the outer loop, and here's the inner loop. Okay, we mean quadratic as in n squared. It happens n squared quantity of times. So theoretically, the outer loop happens n times. You have n integer values. And then this also could, at the maximum, occur n times. So this occurs n times. How many times does it loop through n variables? N. So we have n squared quantity of steps, approximately, that all of these loops take. Of course, we know that it gets shorter and shorter in the inside loop, or longer and longer, but as a general mathematical approximation, we say that it is quadratic. Okay, so now we're done.